Alright, here we go with the Chapter 6 homework review, the last one before this upcoming exam starts. And this homework was dealing with topics related to reactions in solution, which includes an extension of stoichiometry from things we learned in Chapter 5. Looking at the analysis of the assignment, it seems like people did pretty well on the stoichiometry questions. We didn't have any real big problems with those. But the ones I want to go over today are ones dealing with some things about ionic compounds in solution, and especially about redox reactions, which we seem to struggle the most with. But before I start going through homework questions, I do want to do one more balancing redox reaction. This is from the exam review that I did on Friday, March 25th, if you want the date. And there's a technical difficulty in recording my working through this problem, so I want to go ahead and do it here so you'll have it there in the homework review video. If you look at that, the screen is cut off during this question, so it makes it difficult to follow what I'm doing. So here, let's just go through another balancing redox reactions problem. And for this, we need to first assign oxidation numbers. So just like anytime we have a redox reaction that's unbalanced, we're going to assign oxidation numbers, which is going to allow us eventually to balance the number of electrons first before we start worrying about balancing all the atoms out. So if we assign oxidation numbers, this is an ionic compound, so it's going to be, the anion is just its charge, which is -1, and this is going to be a +2 cation. Nitric acid, we've seen this many times in redox reactions problems, so oxygen is -2 and hydrogen is +1 in all acids really, and then that leaves nitrogen as +5 to balance out the oxidation numbers to add up to the overall charge of 0. If we go to the product side, now we have chromium nitrate but with 3 nitrates, so this is a +3 ionic compound, and then nitrate has the same oxidation numbers for nitrogen and oxygen as nitric acid does, so -2 for oxygen and then +5 for nitrogen to give us the overall -1 charge of the nitrite ion. HNO2 nitrous acid, so still -2 and +1 for hydrogen, but we have 1 less oxygen, so that means our nitrogen is going to come in at +3 to balance out all these oxidation numbers. Water, we see it all the time, is +1 and -2. HCl +1 and -1. Alright, so acids, the hydrogen is always going to be +1 and the anion is going to have whatever its charge is. So we have oxidation numbers assigned, and if we figure out which ones are changing their oxidation numbers, chromium goes from +2 to +3, and then the nitrogen in nitric acid is at +5, and there's now nitrous acid, which is +3. So nitrogen is also changing its oxidation number. However, if we look closely at this problem, this is one of those situations where the nitric acid, this species here, is serving 2 roles really. So it is serving as an oxidant because it's changing its oxidation number from +5 to +3, but there's also some other nitrates in the product here with chromium nitrate that still have the +5 oxidation number. So in the case of nitric acid, some of it is being reduced, some of it is not. So just like we've seen a few times before, you have 2 roles, you have 1 reactant with a single oxidation number forming 2 products with different oxidation numbers, and we need to then balance that in 2 parts, which I think is a lot easier way to do it. So we're going to divide this up. We're going to have CrCl2, we have HNO3, which part of it's going to be reduced, another portion of HNO3 which is just serving as an acid. So as very often the case in redox reactions, you don't just have electrons being transferred, you have bonds being broken, or in this case also protons being transferred as part of the reaction. So very often some reactants will serve 2 roles. So nitric acid is one of those in this case, and then the products we just write out as given. I'll leave out all the AQs and everything for now just to balance the reaction. Alright, so a lot of products to balance here, but if we do the number of electrons first, it'll make our life a lot easier. So chromium is going from, as we said, +2 to +3. So that's a 1 electron process. The oxidation number is changing by 1. And then one of our nitrogens in nitric acid is going from +5 to +3. Again, the other one not changing at all. So this is a change in 2 in oxidation number. This is a 2 electron process. So if we're going to balance out the number of electrons, we need to double the coefficients in front of chromium, because each of those chromiums is only losing 1 electron, but we need to have it be a 2 electron process to balance what's happening with the nitrogen. So when we do that, we get chromium chloride. We have to have 2 of them. We have 1 HNO3. We're going to fix that first coefficient to 1. We still haven't balanced the second nitric acid, HNO3. And then we're going to get 2 chromium nitrates. We have to double that coefficient as well to balance number of electrons. 1 HNO2. We don't want to change that coefficient at all. That's already set to 1. And then H2O and HCl. Okay, so when we put coefficients in front of these reactants here, we have to finish out balancing. So if you look at the product side, we have HCl. On the reactant side, we have 4 chlorides as part of chromium chlorides. We need to have 4 HCl's. If we want to balance the nitrogens out, we have 2 times 3 times 3 is 6 nitrates over here, so we need 6 more nitric acids to balance that. And then if we want to finish off with water, we have 7 hydrogens over here, plus 4, we're going to have 3 waters to balance that out. Okay, so each of these, I believe that's correct. Let me check that real quick. Okay, I botched that. There should not be a 3 in front of water. There's only a 1. I was trying to do this on the fly and messed up. But anyway, it doesn't really matter because all we're asking about in this question is the sum of the coefficients on the reactant side. So here we have 2 plus 1 plus 6, our total of 7 nitric acids is going to be 9. So if we were writing this out conventionally, we would combine this 1 and 6 into a single coefficient of 7, but the point is the sum of the coefficients on the reactant side is 9. And we only need 1 water because we only have 1 nitric acid that's losing an oxygen, and that balances out the hydrogen and oxygen just by having 1 water there. Alright, so that's that one. Sorry for the small error, but that's how we do it, and hopefully you can see that better than we did in the review video. Now, 2 of the homework questions we had the most difficulty with also dealt with redox reactions, but in this case we're not actually balancing it. We're already given the coefficients. We just need to figure out which is the oxidizing agent. So remember that the oxidizing agent is the one that is decreasing in oxidation number over the course of the reaction. So we have to find the species where the oxidation number is decreasing. But an important point about assigning oxidizing agents and reducing agents, a couple things. First of all, they have to be reactants in the chemical reaction. We don't classify products using that designation. And also, when we say something is an oxidizing agent, we're referring to the entire reactant. We're not saying one atom in the molecule is the oxidizing agent. If any atoms in that molecule have their oxidation number being decreased, that whole species, that whole molecule, or that whole compound is considered the oxidizing agent. It's not just one atom. So any choice that just has a single atom, B and C, hydrogen and oxygen, are parts of compounds, but they don't exist by themselves, those cannot be the answer. Copper can be, because copper by itself is a reactant here, but hydrogen and oxygen as atoms are not reactants in the chemical reaction, so they themselves cannot be classified as oxidizing agents. Even if the oxidation number of that atom is changing, we're going to assign it to the whole molecule that those are part of. Alright, so to see how this works, we have to assign all the oxidation numbers. Copper is an element by itself, so it's 0. Nitric acid, we see it a lot in these problems, so hydrogen's +1, oxygen's -2, which leaves +5 for nitrogen. We go to the product side. This is copper with 2 nitrates, so it's going to be a +2. Nitrate stays as +5 and -2 for nitrogen and oxygen. We have NO here. Oxygen -2 is the more or less negative atom, which leaves nitrogen as +2, and then our good friend H2O +1 and -2. Alright, so we have all the oxidation numbers. We find the ones that are changing. Copper is going from 0 to +2, and then we have nitrogen. Again, we have 2 roles for nitrogen. Some of them are changing their oxidation number, some of them aren't, but we do have a nitrogen going from +5 to +2. So when we look at this, if we want to assign oxidizing and reducing agents, copper's oxidation number is increasing, which makes it the reducing agent. Sorry, you don't want to put that on the tile line. It's not quite right. But anyway, copper's oxidation number is increasing, so that means the reducing agent is copper. And then the atom whose oxidation number is decreasing is nitrogen. That means the species that contains nitrogen is the oxidizing agent, which would be the entire HNO3 as is written in this reaction. So that's going to be our whole oxidizing agent. Even though nitrogen is the only atom whose oxidation number is changing, we classify the entire reactant as the oxidizing agent. So that will leave us as choice E. So then this next question was very similar to that, and many of us made a mistake that is certainly forgivable, but we want to be aware of the subtlety of why that was the wrong answer. So here we have KBr plus F2 making Br2 plus Kf. So this is called a displacement reaction. And if we assign oxidation numbers here, I forgot to write one of the reactants in. There we go. Okay, so if we write the oxidation numbers in, KBr is an ionic compound, so the oxidation numbers are just the charges of the ions, which are +1 and -1. F2 is an element by itself, no other atoms in that structure, so it's going to be 0. Br2 is an elemental form of bromine, so it's going to be 0, and then we have +1 and -1. So potassium's oxidation number is not changing, but bromine and fluorine are, so Br is going from -1, whoops, too far, -1 to 0, F2 is going from 0 to -1. Alright, so if we want to, I guess this is not balanced. Whoops, this should be a 2, 2. Okay, so now it's balanced. It wasn't given to us as being balanced. But regardless, we still assign oxidation and reducing agents by the change in oxidation number. We don't really care about the coefficients when we're making those designations. So we're looking for the reducing agent, so this is going to be one where the oxidation number increases during the reaction, and we see that bromine goes from -1 to 0. Now that would mean that bromine is part of our reducing agent, and what many of you chose was choice B, Br- as the reducing agent. Now that's not a horrible choice to make, but we have to realize this is not an aqueous reaction, so we don't want to assume that that's the case. We're not told that it's aqueous. We don't have those little AQs in parentheses after any of the species. So if this is not an aqueous reaction, we don't want to assume that the KBr has associated into K plus and Br-. So we can't choose B for that reason. And again, when we're assigning oxidizing and reducing agents, we want it to be the species, the entire molecule, or the entire compound as it exists in the chemical reaction. So that means the correct answer then would be E, which is KBr, because even though potassium's oxidation number is not changing at all, bromine is going from -1 to 0. That makes it the reducing agent, and then we want to assign the whole compound that's part of as the reducing agent. So if this was an aqueous reaction, the story would be different. It would be certainly okay or allowable to assign Br- as the reducing agent, because in aqueous solution it would exist by itself as Br-. But here we're not told it's an aqueous reaction, so KBr is not assumed to be dissociated, and then we're going to pick that whole thing as the reducing agent. So hopefully that distinction is clear now. You have to figure out which atoms are changing their oxidation number, but then it's the entire compound that gets assigned as the oxidizing or reducing agent. And finally, one more redox reaction problem to consider. This is another balancing one, and we want to know the sum of the stoichiometric coefficients on the right side of the equation. So we're going to follow all the rules we know for balancing redox reactions. We have copper 2 plus, I'll leave out all the AQs, they don't really matter for balancing, plus cerium 3 plus. This time water is a reactant, and we're making cerium 4 oxide plus copper metal plus protons H plus. So we need to assign oxidation numbers, and most of these are actually not too bad in this problem because we have a lot of free ions by themselves. So if we have copper 2 plus by itself, that's just a +2 oxidation state. Cerium +3 by itself has a +3 oxidation state. Water, we see it all the time, +1 and -2. We go to the product side, and most of them are also straightforward. Now cerium oxide, oxygen is going to be -2, especially when it's in ionic compounds. There's really no exceptions there. which means cerium has to be +4 to balance out the 2 -2s from oxygen. So it's again an ionic compound where the oxidation number is the charge on the cation. Copper is an element by itself, so it's 0. Hydrogen is an ion by itself, so it just takes the charge of the ion, which is +1. If we go ahead and write out the tie lines and figure out which ones are changing, so copper is going from +2 to 0. So that's a 2-electron process, changing its oxidation number by 2. And then cerium is going from +3 to +4. So this is a 1-electron process. The oxidation number is changing by only 1. So we need to double this. We need to have 2 ceriums being oxidized from +3 to +4 to make it a 2-electron process and balance out the number of electrons from copper. So copper 2+, we keep it as its coefficient as 1, and then but cerium 3+, we have to double. And then we haven't balanced water yet. And then on the product side, because cerium oxide is part of the oxidation reaction that involves 1 electron, we also need to double it. So 2 cerium oxides. Copper we keep as 1 because it's a 2-electron process, and H+. Now we just balance water and H+. So on the product side we have 4 oxygens, which means we need 4 waters, and on the product side we put an 8 in front of H+ to balance hydrogen. So now we're looking for the sum of the coefficients on the right side of the equation. So 2 + 1 + 8 is 11. So that should have been the answer that we chose, which is choice E. Okay, so that's a pretty standard redox reaction to balance. We always start with the number of electrons, balance those first, and then the rest comes from inspection. Okay, this was sort of a little bit of a trick question here. This is about net ionic equations. And we want to know the net ionic equation that describes what happens when aqueous solutions of barium hydroxide and sodium nitrate are mixed. So we should recognize that this is potentially a precipitation reaction. We're mixing 2 ionic compounds together. One of them is a base, but sodium nitrate is not an acid, so it's not going to be an acid-base reaction. And when we mix 2 ionic compounds together, we just need to swap the cations and the anions to make our potential products, and then we have to evaluate their solubility to figure out which one, if any, is going to be a precipitate, or possibly both of them in some rare cases. So if on our reactant side we have barium hydroxide. Now we're told right off the bat these are aqueous solutions. So whether we even know our solubility rules at this point, barium hydroxide is a soluble hydroxide, but we're told it's an aqueous solution, so we assume anyway that it's going to dissociate into its ions. So on the reactant side we have barium hydroxide, which gives us the following ions in solution: barium 2+ and 2 OH minuses. And then we also have, this will take a quick break while my tablet unfreezes. There we go. Alright, and then on the product side, losing my train of thought here. The other reactant is going to be sodium nitrate, which, when it's in solution, dissociates into Na+ and NO3-. So these are the ions available to us, and then for the products we just swap cations and anions. So we're going to have our barium 2+, the cation in the first reaction, combined with the anion from the second reactant, nitrate. So barium 2+ combines with nitrates. We don't even need to really balance this yet. It would be helpful to balance the reaction at some point, but we don't need to right now. And that means one of our products is going to be barium nitrate. And then our other products, we're going to take the anion from the first reactant and combine it with the cation from the second. So our Na+ is going to combine with OH- make NaOH. Now we have to evaluate the solubility of both of these products, because in a net ionic equation we need to have only the ions that are combining to form a precipitate as part of that equation. So barium nitrate is one of our products, and all nitrate salts are soluble. No exceptions to that rule. So this is going to be soluble. If we go to sodium hydroxide, a lot of hydroxides are insoluble, but anything with sodium plus in it is going to be soluble, so these are both soluble. So if both of our products are soluble, we don't have a net ionic equation. We don't have a solid precipitate forming. So if we look at all our answer choices A through D, they all have some solid product here, some precipitate, some insoluble species, and we know that from solubility rules, both of our potential products will be insoluble. So none of these can work out, so the only left answer is E. So in a reaction where you're not forming a precipitate or you're not doing an acid-base reaction, you don't have a net ionic equation. You can mix those two solutions together and nothing will happen. So there's no chemical reaction to even describe here. So that was a bit of a tricky one, but it does sort of allow us to think about net ionic equations. Now another way we could write this, if we wanted to do it sort of in the long form, is if we want to actually balance it out, we have barium hydroxide. Let's actually write it out. Let's write the full ionic equation here. So on the reaction side, we have barium 2 plus. We have 2 OH minuses. Now to balance this, we need to have 2 sodium nitrates. So we're going to have 2 Na pluses, 2 NO3 minuses. And then on the product side, we would have, because everything is soluble, barium 2 plus, 2 NO3 minus, 2 Na plus, 2 OH minus. So in a net ionic equation, we would get rid of the ions that occur on both sides of the arrows, but all of the ions occur on both sides of the arrow. So if we chose to go through and write out the total ionic equation and try to derive a net ionic from it, we would also realize that there are no ions that are changing their form throughout the course of the reaction. Everything is a soluble ionic species on both sides of the arrow. Okay, so that's that one. And then finally, a couple more about concentrations and molarity to close this up. So for this one, this is a question that we sort of give every year, and a lot of students have trouble with it. It's part conceptual, part mathematical, so you have to really think about both angles. I had a little copy-paste there, so that shouldn't be there anymore. Whoops. Okay, so ignore that part of it. But which of the following would produce a 0.1 molar Ki solution? We're given the molar mass. So we're given different masses of Ki, dissolving them in different amounts of water. Now the key concept to realize for this question is that this big M here, molarity, remember that it means moles of solute, which in this case is Ki, per liters of solution. So when we make a solution that has a specific molarity, we can't just add a certain amount of water to it. That's our solvent. We have to make sure that our solution volume is equal to whatever desired volume we want for that solution. So that's a key point. Now, in real life, the solution volume is not going to change a lot. The volume of the water is not going to change a lot when you dissolve something in it. But practically speaking, we don't have we don't necessarily have additive volumes. So if you make if you add 1 liter of solvent, you're not necessarily going to get 1 liter of solution, because the solution density is different than the density of the liquid by itself, even though in most practical cases they're not that much different. So the point I'm trying to make here is some of our answer choices we can eliminate right away, because in choice A, we're taking some amount of Ki, but we're adding just 100 milliliters of water from a graduated cylinder. And if we're going to make a solution with a specific molarity, we need to make sure that our solution volume is a known amount. And then the same with choice C. Choice C, we're taking 0.1 moles of solute, but we're just dissolving it in 1 liter of water, not making 1 liter of solution. So it's a very minor and very subtle distinction, but it is an important one. And that means that we have to evaluate choice B, D, and E, because all of these we're making a solution of a specific volume, and we need to see if either of these have the correct molarity. So for choice B, we have moles of Ki per liter of solution. So the moles of Ki are going to be, we have 3.32 grams. So for all of these, we're going to convert grams to moles by just dividing by the molar mass that we're given, which is 166. So choice B, we've worked this out. This is 0.02 moles exactly. So when we divide that by the volume of that solution in choice, in that answer choice, eventually. Alright, so that's 0.0200 moles. And the volume of the solution in choice B is 50 milliliters. So that's going to be 0.050 liters. We move the decimal place over 3. And we can see where this is not going to equal 0.1. This is going to be 0.4 molar. Okay, so choice B is out. The concentration of that solution is too high. If we go to choice D, we can do this one in our head a little bit, because choice D, we have 166 grams. That's equal to the molar mass. That's going to be 1 mole. And we have 1 liter of solution. So 1 mole per liter is 1 molar. We can do that math in our head. So choice D is wrong. So hopefully choice E works out because we've eliminated the rest. And if we look at the numbers given to us in choice E, the moles of Ki are going to be 4.15 grams divided by the molar mass. So we get 0.025 moles, which means the concentration is 0.025 moles, and then the volume of this solution in choice E is 250 milliliters, which is 0.25 liters. And that's going to give us 0.100 molar, which is the number we're looking for. So choice E works out. So there was a lot of work involved with this one in terms of calculating all the different concentrations, but 2 of them we can eliminate, because if we're making a molarity, if we're making a solution with a specific molarity, we need to know the volume of the solution, not just the volume of water that we add to make that solution. Alright, so finally one more molarity question. A solution has 10 grams of sodium carbonate in 2.33 liters. What is its sodium ion concentration in moles per liter? So whenever we make an aqueous solution, specifically one with an ionic compound, we have to look carefully at what concentration we're actually defining as part of the problem. So here we're looking for the sodium ion concentration, so we're looking for the molarity of sodium ions, which is again going to be the moles of Na plus over liters of solution. Now we're given the volume of the solution is 2.33 liters, so that we already have, but we also need to then find the moles of Na plus that are contained in 10 grams of sodium carbonate. So this is just a mole conversion, something we've been doing since the beginning of chapter 5, but we have to remember that we're looking for the moles of sodium ions and not just the moles of the compound itself. So we first need the formula for sodium carbonate. So sodium carbonate is Na plus paired with CO3 2 minus, mix up the 2 and 3. So that's going to give us Na2CO3. So the formula for sodium carbonate is Na2CO3, which means we need then the molar mass, this script M, is going to be, so we calculate that out, it's going to be 106.08 grams per mole. So once we know the formula, we can get the molar mass, which we're going to need because we're converting from mass into moles. So now the moles of Na plus, we have 10 grams of sodium carbonate. We convert to moles first by using the molar mass, which we just calculated is 106.08. All right, now this is moles of sodium carbonate, but we're looking for moles of sodium ions. So from the formula Na2CO3, we know that when we dissolve sodium carbonate in water, we have 2 moles of Na plus for every 1 mole of Na2CO3 that dissolves. And again, that comes from the formula for the ionic compound, which has a 2 after sodium. So there's 2 moles of sodium per mole of compound. And so when we multiply this across, we get 0.189 moles of Na plus. So we put that back up here into our molarity formula. We divide by 2.33, which is the volume, and we get a sodium ion concentration of 0.0809 molar. Okay, so when we have ionic compounds, we can define concentrations for each ion individually, and we have to take into account how many of each of those ions are in the compound that we're dissolving. Alright, so that takes us through this week's homework review. Please come into my office and ask me any other questions you have, or send me an email, whatever is convenient for you, and I will see you next week on the YouTube.